Today we're going to do a mini lecture on Atwood machines. So what is an Atwood machine? Well, the first thing we have to know is that if we have a thing called a pulley, it changes the direction of force. Right? So if I have a mass here, right, and I have another mass here, well, what force does this mass apply on this one? Well, we start off by pulling down this way, right? The mass is pulled down by gravity. But then, right, this block is actually pulled up this way by this block. Even though we applied the force this way, right, the resulting force is this way, because the pulley changes the direction of our force. If this is our force vector, right, it goes around the pulley like this, and now it faces in the opposite direction. So, Atwood machines are just like things with masses, and we have pulleys on them. So, masses on pulleys, let's say we have like this, right? This is the first Atwood machine we'll consider. And let's say this is M1 and this is M2, right? And let's say that positive force, positive acceleration, positive everything is going to go in this direction, so this direction is positive, and if the blocks are pulled in this direction, it's going to be negative, right? This might look like the same direction, right? But if this mass is bigger, the whole machine is going to go like this. And this is what we'll call positive acceleration. The system starts accelerating this way. If it goes in the opposite direction, like M2 is bigger, then the system is going to go like this. And this is what we'll define as accelerating in the negative direction. Alright, so now let's try to find what the net acceleration of the system is. Well, to do that, we have to find all the forces that are acting on the system. We'll assume this is an ideal pulley, right? So there's no resistance on it. It doesn't take any force to rotate it. It's an ideal pulley. There's no moment of inertia, nothing. That means these two are the only things, these two objects are the only things that are acting on the system that have force. Or the two objects in the system, so we'll draw a Freebody diagram for each one. This one has a weight on it, which we'll call FW1, which is just M1G. And this also has some tension that's pulling up on it. Right? The tension on the string is pulling up, T. Well, what is this T? This T is going to be equal on this side, right? Because this tension is the thing. This is the force that M2 applies on M1, right? It's pulling the string, it pulls up on it. We assume the string is ideally distributed, so that means all the tension is equal along the entire string. Right? So the force M2 applies on M1, according to Newton's third law, is the same as the force M1 applies on M2. So this tension, which is the force M1 applies on M2, is the same. And then the force, gravitational force on M2, or the weight, is equal to M2G. Alright, so we've drawn the free body diagram. And now let's add all the forces that go in the positive direction and all the forces that go in the negative direction. Remember, positive direction is as if the system is rotating this way. Right? So anything going in this direction is positive. What's positive? This is positive, right? It's going this way. This is positive. So we'll add FW1 plus T. This T is positive. What do we subtract? Well, this T is in the opposite direction. It's as if it's going this way. So we subtract T. And we also subtract FW2, right? So that means the net force on the system is equal to F1W1 minus FW2 because the T's cancel out. So I get FW1 minus FW2. And let's write this out as M1G minus M2G. Now let's stop and think. Does this make sense? Well, let's say that M1, right? M1 we'll say is bigger, right? Let's say the whole system is going in this direction. Well, then we can say that M1 is just M2 plus some extra mass, right? If I remove this extra mass, the whole system would be balanced. The forces would be the same. So the two things would just lay at rest. Nothing would happen. There'd be no rotation. The two masses would just lie idle. All right? So the force of change, as soon as I add this extra mass in, this extra mass m, the whole thing is going to start going down this way. And so that means that the whole force on the system, that force on the system, is only applied by this mass m. What is the mass m? The mass m, m plus m2 is m1, right? So the mass m is m1 minus m2, right? Because we can say m plus m2 is equal to m1. So m1 minus m2 is equal to m. And what is the weight of m, or the force that m applies? Well, that would just be this whole thing multiplied by g. Right? And that's what we have here. So that's why it makes conceptual sense to say this. Yeah, so when we do this, it doesn't matter if m1 is bigger or m2 is bigger. because the direction, if it's positive, right, that means the force is going this way. If it's negative, that means the force is going this way. This should be M1. Alright, so then we remember Newton's second law, which says that force is mass times acceleration. So that means acceleration is force over mass. So F net over the total mass of the system. What is that? That's m1g minus m2g divided by the total mass of the system, which is m1 and m2, m1 plus m2. That is our net acceleration on the system. Oh, there should be a g here. There we go. Awesome. So that was the first Atwood machine we'll look at. The second one we'll look at actually has to do with friction. There's some frictional component applied on the second Atwood machine. So let's look at this one. I have a block here, and I have another ramp here. Here I have a block of mass 1, and here I have a block of mass 2. And let's assume mass 2 is bigger because I drew it bigger, or has a bigger mass here. And there's a pulley. This one's angle of repose on here is sine theta 1, and here we have theta 2. What is the net acceleration of the system? So let's assume that they tell us that the whole system is moving this way. Right? Is moving this way in this direction. Well, what are all the forces that are acting on M2? Well, let's look here. M2 we have, its gravity pulls it down straight, right? We have gravity that pulls it this way. We have the frictional force, right? This object is moving this way, so we have its friction that goes this way. And then we have the normal force that goes perpendicular to the surface. And do we have any other force? I don't think so. What about M1? Well, for M1, right, we have gravity pulls it down. What else do we have? Gravity pulls it down, the normal force pushes it this way, and then we have friction. Which way does friction act? Well, the object is moving this way, right? So that means the friction has to oppose its motion. So friction is actually going to go in this direction, F of 1, or friction 1, small f. Alright, this seems really confusing right now. So what we're going to do is we're going to simplify some things. Right? So we only want to consider the forces that are going in this direction, that are in this direction. Because the object is not moving this way or this way, right? It's only sliding this way. That's because the normal force and this component of gravity acting against the normal force cancels out. So we don't have any forces this way. So let's only consider the forces in this direction. Well, one force in this direction, right, is this component of gravity. So we can say, right, what we know is we know that this angle is theta 2. If you saw the last video, you'll know why. But we can do some basic angle chasing to find out why. Here's the right angle. Here's theta 2, 90 minus theta 2. Here's theta 2, and this is a right angle. So that's why this and this has to be theta 2, given this is 90 minus theta 2. All right. So if this is theta 2, that means the this component of gravity is equal to m2g multiplied by sine theta. Oh, I'll write a big disclaimer that m2 is bigger than m1, and we are moving in this direction. There's motion. Because that is actually important in the problem. Next thing we want to find is F2. Well, F2, right, from last video we know, F2 is equal to mu k, right, because it's moving, multiplied by F of n2. What is F of n2? F of n2 is equal to, F of n2 is equal to m2g cosine theta. So we're subtracting this friction because it's going in this direction when we only want motion that goes here. So we are subtracting m2g, or mu times m2g times cosine theta. Alright, so we have mu k m2g cosine theta. Alright, what else? What about this side? Right? So forces going this way are good. Right? So that means forces going up this way, right? Because the pulley changes the direction of the force. So any force going this way is going to go up this way are positive. If you note, we actually don't have any positive forces in this direction. We have negative forces in this direction. So what more do we have to subtract? Well, we have to subtract this component that's in this direction, right? Because it's pulling down this way. So we'll subtract, and that would be m1g sine theta. sine theta 1. Oh, this is theta 2 because we were working on this side with only this angle, theta 2, theta 2, theta 2. This time we're working with theta 1 because this angle is theta 1. And we can find that because we can do a little bit more angle chasing. This is a right angle. This is 90 minus theta 1. I'm going to write pi minus theta 1 to be edgy today. And then here is theta 1. Alright, and what is the last thing we need to find? And now what is the last thing? Well, the last thing we have to do now is, oh, by the way, we're finding the net force right now. The last thing we have to do is subtract this. Well, what is that? This is equal to theta mu k of 1, the kinetic friction force of 1, this mass 1, multiplied by m1 g sine, or cosine of theta 1. And we can get it in the same exact way we got this one. And how did we get that one? Well, we want to find f1 is equal to mu k1 times f of n. What is f of n1? F of n1 is equal to m is equal to fw multiplied, because these two forces balance out because there's no force moving it this way or this way. So it's equal to this component of weight, which is m1g multiplied by cosine of theta 1. Right? Theta 1, cosine is this over this, so we can rearrange that in order to find this relationship. Then we plug this into here, and we get this. If this is the net force, what is the acceleration? Well, acceleration means we divide the whole thing by the total mass of the system. What is the total mass of the system? Well, the total mass of the system is just the sum of all the masses that we see in our system. What masses are those? M1 and M2, or M1 plus M2. So for this kind of Atwood machine, here is the general equation for what is the net acceleration. So if College Board ever decides to ask this for some reason, this will be your answer. Good thing to have it on your equation sheet, just in case. We never know what they'll ask. So for now, I hope you enjoy your studying, and yeah, until next time, have fun, and yeah, keep working hard studying.